This is 126, and we're down to debugging, I think kernel debugging today. Yep, kernel debugging. So let's start with that, and then I'll demonstrate some of the projects that go with it. So WinDebug is the tool from Microsoft that is hard to use, but it's very powerful. It's intended to be used to write Windows drivers and such. So you can run it in user mode or kernel mode. OllyDebug is popular and a more modern version of it, Immunity Debugger, but it only does user mode debugging. You cannot debug the kernel. So, to understand what's in the kernel, device drivers are in the kernel. Now, this is a problem with the Windows security model. When you buy some piece of hardware, like a printer, the manufacturer of the printer has to write the driver because they know what electrical signals have to go out to make the printer do things. And so they write the driver, but then the driver has to run in kernel mode because only in kernel mode does any software have access to the hardware. So Microsoft doesn't really control all the code in the kernel. And often the drivers are poorly written and crash, and it causes most of the blue screens of death, and Microsoft doesn't like it. So drivers are loaded into memory, they stay resident, they listen to requests from applications, and of course you can't directly access kernel drivers, you access things called device objects, which send requests to the kernel drivers. So devices, remember everything in Microsoft is always named the opposite of what it is. So a device is not a physical hardware device. It is a software representation of it. So a driver creates and destroys devices, which you then access from user space. So they create a printer device, which is a software device you print to. So if you plug in a USB flash drive, Windows creates the F drive device object. Now you can read and write to the F drive. You plug in a second drive, it will use the same driver to create a new device called G, which you can write to. So that's how it works. And that's why there's a record in the registry of every USB used plugged in, because it keeps track of what drivers it's loaded. So DILs are loaded into processes. If you run an executable and you need a DIL, it calls up the DIL, loads it into memory, runs DIL main to get it ready to go, and then it's available to use the functions that have been exported from that DIL. Drivers have a similar process. Drivers have to be loaded in the kernel. So when a driver is first loaded, its driver entry procedure is called. This prepares callback objects, which are like exports. So there's different terms, but it's a very similar kind of process. So you define a callback object, and then your objects in memory, your programs call that to access the device. So DILs, loaded in memory when a process is launched, execute DIL main at the time they load, and have an export table. Drivers load into the kernel when hardware is added. They execute driver entry to get them ready, and they prepare callback functions and callback objects. So driver entry, DILs expose functionality through the export table, but drivers don't. They must register the address for these callback functions. And that's what driver entry does. Creates a driver object structure, passes it to driver entry, and then creates a device that can be accessed from user land. So normal read request, your user mode application obtains a file handle to the device, calls read file on the handle. The kernel processes the read file request. It actually goes to the hardware like a hard disk to read it, and then it invokes the driver's callback function to do that. So malicious request. You most commonly use device I/O control. This is a generic request, and your user space program can pass in a buffer of data and receive a buffer of output data. This is a low-level call directly to a device. So malicious programs are here, and they go to kernel 32, which is a user land, and then ntdil, which is in user land. Then they go into kernel land, where the dashed line is. This is the kernel itself, NTOS kernel, but it also has drivers, and other drivers out here are going to the hardware. So this is how user mode calls are handled by the kernel. You make a call, it passes through this chain of objects to get to the kernel. There is some kernel mode malware that doesn't connect to user mode at all, but that's not that common, especially not in modern versions of Windows. So NTOS kernel and hal.dil. NTOS kernel has the code for the core OS functions. Hal.dil is the hardware abstraction layer. So it has code to interact with main hardware components like the motherboard. Malware will import functions from these, so it can manipulate the kernel. Let's take a look at a Kahoot. This has got to be 10A. Good. For some reason my monitor won't let me see how many people are in Twitch. I guess there's some people. All right. All right, so what can applications interact with? Send data to a device. The device then sends it to the kernel where the drivers are, which then goes to the hardware. All right. What code is loaded into a process? DILs. Libraries are loaded into processes. We've been doing it all semester. All right. All right, when a driver is loaded, what procedure is first called? Driver entry. Not DIL main because it's not a DIL. Those are libraries. Driver entry is the first thing called when you load a driver. All right. So which one of these things runs in user mode? In user mode because everything always has the wrong name. The kernel is NTOS kernel. And HAL and the drivers, all the others that are in the kernel mode, this is the only thing that runs in user mode, the thing named kernel, of course. How could that be confusing? Anyway. And by the way, I should mention, if you're a Microsoft insider, you call WinDebug Windbag. That's their internal joke. And Microsoft is a cult group. They're all full of things you have to do to show you're inside the cult group. So it's, if you want to work at Microsoft, you have to sort of adopt their religion and believe a lot of false things or pretend to believe a lot of false things. Anyway, so kernel debugging. In VMware, you enable kernel debugging in the operating system, and if you want to control it with a second machine, you configure a virtual serial port between the virtual machine and the host. We're not doing it that way anymore. Thank God, it was very painful. Boot.ini, the book refers to boot.ini, but now it's BCD edit, but it doesn't matter. You go to BCD edit and turn on debugging. Then this machine can be debugged by another machine through a serial port, or these days an Ethernet port or other things, but we're going to do single machine debugging for what we're doing here. So you install WinDebug, and I've got various instructions. We'll talk about it later. You can download it directly, except on ARM machines, you have to install the software development kit. You cannot download WinDebug separately and have it work. Anyway, you install the software development kit. This is the way you do it for ARM. You install debugging tools for Windows in here. That's one way to get it. You can actually download it, WinDebug alone directly now. It's in the links and projects I updated today. I see a comment in the chat. I am WinDebug, but I'm not taking the class. Okay, good. All right, fair enough. Good. Thanks for telling me. All right, so LiveKD is what you use if you are running on an Intel processor, although I'm not sure it's even necessary anymore, because when I made it work for ARM, you didn't need it. But anyway, you can use LiveKD. All right. And then you can look at the kernel. It'll load up and tell you things about symbols, because you can the running version of process of executables that make the operating system go do not contain symbols, but you want symbols for debugging, and so it downloads them from Microsoft, and you have to get exactly the right symbol thing, and it takes a while, and it doesn't find it for all of them. So anyway, there's command line commands in WinDebug. DA will display an address of region of memory is ASCII, DU is Unicode, DD is 32-bit hexadecimal words, or DA to show the ASCII text, and then there's DB to show both ASCII and hex. All right, you can edit memory. Here you can write, although not with what we're going to do here with single user mode, not in the kernel. Anyway, you have arithmetic operators, so you can refer to an address and add or subtract from it. So this will show the first argument for a function. DW will read the value at a 32-bit location pointer, so this will go to the stack +4, and then find the value at that location, and that will be the first argument for a function. Remember, when you call a function, the function starts, and then it looks on the stack and assumes whatever's on there are my arguments. It doesn't know whether you actually correctly set it up. So if you call print, it prints whatever it finds on the stack. And if you forgot to load anything sensible on the stack, it will print whatever it finds there, which may be something you don't really want printed. So you can set breakpoints. You can specify an action. So you can do something like this. You can set a breakpoint when this get process is called, and when that happens, immediately do this. Dump ASCII, the second argument on the stack, and then resume execution. This is pretty cool. This is why WinDebug is really powerful. You can write a script like this that will do something like, for example, every time it opens a file, print the name of the file, so I know what files it's using for things like that. This is pretty cute. But there's you can't use any of those breakpoints with LiveKD or the kind of debugging we're doing here, though, because we're debugging the running system. All right. Although we will use them in userland debugging, you can't use them in kernel mode debugging or you'd freeze the whole machine. List module shows all the modules, and it shows you all the kernel drivers in kernel mode. This is as close as you get to a memory map. Unfortunately, there is not a view memory like there is in Ollie debug that shows you everything. So load list modules for module named disk will show the disk driver, and here it is, C symbols disk. Those are the symbols, and there's a module named disk. It shows you the address where it starts, the address where it ends, and here's the symbols it found for it somewhere. So you'll be able to refer to symbols inside that object. You can read. ZTNT will show the start of module NT. This will show the first 10 words of NT. This is a hexadecimal number, so it's the first 16 words of the NT module. So here you see DDNT. That just shows you some default amount of the bytes starting at the NT. This is NTOS kernel. And here it is showing me the first 10 bytes, and 10 is 16 because it's hexadecimal. So I get 4 groups of 4. All right. .hh shows you help. This is the Windows 3.1 chum file, help, which is the way you learn WinDebug. This is the best documentation available. It's the place to go, better than any textbook. This is where you learn how to use it. You have to read these things to find out what the switches are and how they work. And they're often very confusing and unintuitive, so you have to get used to referring to this thing quite a bit when you're new. And R will dump out the registers. So anyway, there are online tutorials too, but that help system built into WinDebug is really your best friend. Let's try another Kahoot. Can the old WinDebug from Windows 10 SDK in a Win 10 work together with the preview? Well, if it's in a different Win 10, yes, but what I found was I don't know about the old one persisting with the preview one. The preview one is no longer called preview, and if you install the new one on the preview one, it will overwrite it and erase it. I'm not sure about the old and the new one being together on the same system at the same time. I haven't tried that. All right. 10b. So which command will set a breakpoint? BP, that's pretty obvious. Which command will show memory contents as ASCII characters? DA, dump ASCII. All right, which command will show kernel drivers? Load list modules, LM. We'll do it if you're in the kernel. All right, which command will change memory? Ed will edit a dword value in memory. Good. All right. So Microsoft symbols, I mentioned them before. The symbol table will let you refer to things by their alphabetical symbol name instead of just an address, which would vary. So you'd have a create process address space, a label, perhaps the name of a function or the name of some other numbered area of memory. So you have a module name, bang, symbol name. So you'll see things like NT bang, NT create process. This will go into the kernel itself, NTOS kernel, and then it will find the beginning of the NT create process function, which is one of the kernel modules you can run. This will unassemble that function with a U in front of it, and that's how it works. So you can unassemble NT create process, or you can do it with length of 10 or length of 20, and it'll show you the contents. And we'll do this kind of thing later in the project, and you saw it last week too. So BU will set a breakpoint as soon as this module is loaded. IMENT will find the entry point of a module, so you can break at the IMENT of driver name, and that will break on the entry point of the driver before any of the code runs. So you might do this if you need to know when a driver loads and you want to examine that driver before you let it run because you think something's wrong with it or you think it's malicious. See, X is what you use to search for symbols. So you can do X, search the NT function for anything that contains the word create process, and so you'll get all these functions that have the word create process in there somewhere, which is very useful. You can list the closest symbol. With an address, you can do LN, and it will show you the closest thing to it. So I look at this address, and it finds NT read file there. And there's another thing it finds later. So that's pretty cool. You can view structure information for a C++ data structure, which is used a lot by drivers and pretty much every program, which is why I say Microsoft cannot really hide anything about Windows from hackers. By using WinDebug and looking at the kernel, you can see exactly what Windows is doing. It really almost might as well be open source. If you learn how to do this, you can see exactly how everything is handled. You can figure out the undocumented functions and everything else. So here you view the type information for a driver object, and here it is. It's a device object. It's got the name as a Unicode string, hardware database, and various other things are here, or driver size, and so on. All the pieces of it are there. And so you can do driver object and device object. Here's what a device object looks like. Next device, attached device, timer, characteristics, and so on, all these various objects here. All right. And you can then look at the beep driver. I don't know if this is still around. It used to be long ago in MS-DOS, you would type Control-G and it would go beep. And that is still in Windows. I'm not sure under what circumstances it's called anymore. But you can look at the beep driver. And here's a long beep, driver entry. So anyway, Unicode string, driver beep. It's in there. It's part of Windows. And driver init is the function called when a driver is loaded. So you should be able to see the driver init here. And here it is. The labeled line is the driver init address, which is part of the structure, or part of the information about that driver. All right, and this is what we saw when we made malicious dills with Metasploit. It just put all the malware right in dill main. So it would just be called as soon as it loaded. And you can do the same thing with drivers. A malicious driver might just put malware right in driver init, so it'll just be called as soon as the driver is loaded. All right, if you're connected to an always-on broadband link, you can configure WinDebug to automatically download symbols from Microsoft and cache them, which is the normal way you use it these days. You can also manually download them and save them on your drive, which is what you might do if for some reason you're working in isolation from the internet, which almost nobody does anymore, but it is possible. So we're now to 10C. It. All right. All right. I think we already did this one. Sets a breakpoint? Oh, I guess not. Okay, good. That's right. Different set of answers than last time. Okay. This will break when it loads that driver. All right, which command shows type information for a structure? This one, display type of that object, all right? And which one lists all the functions in NTOS kernel? Yep, this one, examine NT bang star will show me everything in there, every labeled object, including all the functions. So, in practice, we're going to look at a program that writes files from kernel space, which is an unusual thing to do, a piece of malware essentially. Kernel mode programs cannot use create file and write file because those are user mode programs. They have to use NT create file and NT write file. So the user space code will create a service to load a kernel driver. So here it's going to define the service type with the create service function. Service type is 0x01, kernel driver. Then it's going to go down here and push that up there and create file. All right. it's pushing. Remember I talked about how you call a function. You push all the arguments on the stack, then you call the function, and it will look on the stack and expect to find the file name here and the attributes up there and so on. Once it has a handle to the device, it uses device IO control function here to send data to the driver. So it's going to load on the stack, push, push, push. It's going to push all the stuff on the stack, including the data it wants to send, and then call the device IO control. So kernel mode, if you want to do this, you set WinDebug to verbose mode, and then you'd be able to see every kernel module that loads. Kernel modules normally load only when new hardware appears, so if they're loading frequently, that is something suspicious. When using VMware, you will see K-mixture loaded and unloaded. That's normal. Right, so drive object shows the driver object here. Bang drive object for file writer. Here's the driver object. Tried to load symbols, but it couldn't find the symbols. And so it shows you some information about the driver, which is here. Here's the driver object, showing, as usual, all the things in here like the driver name and so on. Details of that object, the structure. Right, so it eventually creates a file, DOS devices C secret file.txt. Remember, it has this funny path because it doesn't go to the normal drive letter, it goes to like the root of the hardware this way. This is called a fully qualified object name. And, all right, applications work with devices, not drivers. So you look at the user space application to identify the device object, then you look at that device object to find the driver object, then you go to dev object to find more about the device object and dev handles to find the applications that use the driver. That's how you can trace down what's using a suspicious driver. And then there's rootkits. Rootkits modify the internal functionality of the operating system to hide things like processes and files and network connections. And the idea is once they've done it, then your antivirus can't find it because it tries to scan all the files, but the rootkit hides some of the files from it. Now this is the most popular method, at least up through Windows Vista or so. I'm not sure any modern version of Windows will let you do this anymore. That's why I got rid of the projects where I actually did this. The SSDT table hooking, system server descriptor table hooking, is where you modify where the API calls are going to go. And this still works on Linux. When you do 127 class, we're going to use this technique effectively to hijack system calls to Linux programs, but you can't get away with it in the Windows kernel anymore. So this is used internally by Microsoft to look up functions. And so there's the user space can access kernel code by doing a syscall. And syscall, sysenter, and int2e are just different versions of the same thing. So that'll call sysenter in modern versions of Windows. The function code is stored in the EAX register. So you do a syscall, it looks at this number, and that number tells it whether you want to read or write or do other things. So here, for example, in ntdil, you've got sysenter here. So you put 25 in EAX, then you prepare some other things, then you call sysenter. So 25 is create file. So this is going to create a file, and you must have prepared the stack pointer, saved in EDX, called sysenter. That's going to create a file, and someplace you must have put the file name on the stack. So then it's going to call the SSDT. Goes to item number 25, and that's going to have the address of ntcreateFile. This is how it works with layers of indirection. And it has to do this because you might have a Windows update, and the Windows update might make ntcreateFile longer, and then it won't fit where it is, and they have to move it somewhere else, so they have to change this address. So this way you can modify things and just change the address in this table, and all the programs that are already installed will find that function. So you could go in here and change this to point to some malware, and then when programs try to call ntcreateFile, they'll really be calling a malicious function. And when we do this in Android, we call it instrumenting. It's modifying the API calls so that existing programs now do different things than the designer intended for them to do. It's pretty cool. But you can't do it very easily in Windows anymore. You used to be able to do it pretty easily in Windows XP and such. Microsoft got fed up with it, and they put in a lot of defenses. So a rootkit would call the original ntcreateFile, then remove the files it wants to hide. However, if you only hook ntcreateFile, that will not stop dir from seeing your file because it doesn't create a file, it uses a different function. So you'd have to hook some other functions too to fool that program. So the simplest way to detect this is just look at the SSDT table, and you'll find inappropriate addresses. In my machine, when I did this, the kernel goes from 804D to 806C. So those are all the kernel addresses. So every entry in the SSDT should be in this range. And so you can list all the modules in the SSDT table, and you can see here's good values. From 824 to 825, those are all pointing to the real kernel. But if you have a malicious one, it'll be pointing somewhere else, like F7. So, all right, you can tell it's just not pointing to the kernel. All right, so LM shows you the modules, which are all drivers, and you can list the rootkit hook function. Okay, so the hook function is here. It's going to call the original NT create file function for some requests, and for others, it's going to return this value 34, which is like not found. So it's going to go through an if statement, and if it likes the program, it's going to call the selected NT file, create file. If it doesn't want to let you create that file, it'll tell you it can't. That's the sort of thing you do to win rootkits. Now, interrupts allow you to interrupt processing and have something done out of order for things like key presses and mouse movements and such. So you specify an interrupt service routine to be called when it happens, and there's an interrupt descriptor table, which shows where the various interrupts go. So here's the interrupt descriptor table showing various things that can happen: a PIC spurious service, port interrupt, serial port, SCSI port interrupt, IDE port. These are the input channels for various hardware that might demand that they need some service right away. You can load a driver to test it. There's a driver loader tool available. And I've had some earlier versions of this class. We made drivers and installed them and stuff. We're not doing it this semester. Like I said, it's gotten much, much harder. Microsoft has added a lot of driver security to Windows these days to stop people from sneaking in malicious drivers. So BCD edit has replaced boot.ini, and now they have PatchGuard, which prevents third-party code from modifying the kernel. This is everything since Windows Vista, and the 64-bit version has not let you change the SSDT or IDT anymore. Like I say, so, all right. And driver signing is now enforced in all versions of Windows. So only digital assigned drivers will load. You can turn it off with the BCD edit command to reboot in a mode that will not enforce signed drivers. But the default is to enforce signed drivers, and that's why I say our kernel malware is practically non-existent. These kernel mode rootkits, they're very hard to write, and you don't see them much anymore as far as I know. All right, let's try the last Kahoot. It's 10D. Security software, like antivirus and firewalls, all used to work by modifying the SSDT and hooking functions. Well, Microsoft got fed up with it. Everybody just started doing this all the time until they were losing control of the kernel. And they put a tool in Windows XP to tell them when your machine crashed, why it crashed. And by watching that, they found out that most blue screens were caused by third-party drivers. And that's when they started putting in all this crackdown on all the lousy driver code.
Actually, it's a combination of both third-party drivers and problems with the hard drive. Because back in the day, they were using the hard drives that were not solid state, and they would wear out in about a year or two.
Oh, I never had that happen. Yeah.
Because I was buying cheap PCs from Costco, and the hard drive life expectancy was about a couple of years.
That's pretty harsh.
So what would happen, unfortunately, I bought a PC, a cheap pavilion that was a hybrid. He used the hard drive from Sony Bio. He used a motherboard from HP, or from Hitachi, and something else from somebody else.
Well, a Frankenstein like that, you're going to have trouble. Yeah.
And that thing would just start doing molecular grid or blue screen of death. And I couldn't figure out what it was until I figured it out.
Yeah, I had a crappy homemade machine like that, and then I tried putting Linux on it. Of course, nothing worked.
I was able to put Linux on it. The way I used to do it is I had to break boot and load command line. Never load GUI. You load GUI, you would install on the hard drive, with erase Windows XP, and then you would BSOL.
Yeah, yep.
This is what basically I was supposed to do, build a Linux firewall using Slackware. And I ended up failing that class because I couldn't do it.
Yeah, that's pretty harsh. Virtual machines are so nice these days. All right.
But all the computers going from something like they're going to show you the Lenovo PC for 4 gigabytes of space.
All right. All right, so which module is loaded and unloaded by virtual machines? Mixer. All right. All right. What's the normal function used to execute kernel code? Sysenter is the modern way to do it. Syscall is a term that is used to generically refer to this, but the actual command used now is sysenter. All right, what object is most commonly ordered by rootkits, at least before Vista? SSTT, so you can change what the system calls do to instrument your Windows machine. All right, which one is not used in Windows 10? Boot.ini was used to control boot up in XP and earlier, but now it's BCD-edit that does that. All right, which one is required to use unsigned device drivers in 64-bit Windows 10? You have to turn on no integrity checks using BCD-edit and reboot. You can reboot into a special mode that will let you run unsigned drivers. They make it difficult because they really don't recommend it. All right, and there's no new comments in the chat. I'm going to stop the recording.